Hello, I'm Erik, and I'm going to talk with you today about graphs and our plan for building a faster NetworkX-Like library for Python. So I think we all have an intuitive understanding of what a graph is. If I ask you to draw your friend network, you will probably draw nodes as friends connected by lines to indicate relationships, like what we have here in the upper right. Remember, edges in graphs can be directed or undirected, and nodes and edges may have weights or data. Great. So what's the big picture? This is the most important slide in the entire presentation. It tells you what you need to know, which is that GraphBLAS is groovy, but NetworkX is who you want to go dancing with. GraphBLAS, in addition to being a saxophone playing flower, is a really fast C library that enables us to write graph algorithms. Our first library here, Python GraphBLAS, makes writing GraphBLAS as natural as it can be in Python. Of course, we wrap the C library, but we actually target the mathematical language behind GraphBLAS, which leads to some pretty interesting Python syntax. Our second library here, GraphBLAS Algorithms, uses Python GraphBLAS to implement the NetworkX API. It's pretty new, and we only have a few algorithms so far, but hopefully it'll be a dancing cactus soon and match NetworkX. Okay, let's jump right in. This is a talk at a Python conference, so let's look at some Python code. This shows the core of three algorithms: single source shortest path, and two variants of breadth first search, one that returns levels and one that returns parents. So please don't panic. I don't expect you to understand this yet, but I do want to point out a few things as you're looking through the code. First, A here is a matrix, and frontier is a vector. We're doing a fancy sparse matrix multiply using the matmul operator, which is the @ symbol. Min plus here changes what we mean by matrix multiply. And we're accumulating results back into the frontier vector here on the left-hand side using the min binary operator. In breadth first search, we see tilde level.s on the left, which indicates a complemented structural mask. I don't expect you to know what that means, but in breadth first search, you only need to visit each node one time. So using a mask here lets us ignore nodes that we've already visited. Doing this is very important for being work efficient. The last thing I want to point out here is that each line, Python line, corresponds to a single GraphBLAS C call. So like we're building up expressions as we go along. There's a lot more to GraphBLAS, but I hope this at least gives you a flavor of our syntax. Now, why do we even care? And more importantly, why should you care about any of this? My short answer is that graphs are everywhere and used by everyone. This answer is a bit hyperbolic, of course, but only slightly. Graphs really are everywhere because relationships between things are everywhere. Theoretically, graphs are among the most important and most general abstract data structure in computer science. It's applied in science, engineering, finance, commerce, military, and so on. Pick a field, and I bet graphs are used somewhere, such as for maps or social networks, neuroscience, biology, genomics, chemistry, fraud detection, image analysis, data science, recommender systems, graph neural networks, optimization, disease propagation, knowledge graphs, power grids, even everyday business queries and business logics or analytics, and so on and so on. Whew, it's a mouthful. You don't need a PhD in graph theory to use graphs. I would say the majority of people who use graphs have some other domain of expertise. This means that graphs as a skill is available to anybody and is valuable. It's also a rewarding community to get involved with. Because it's so interdisciplinary, you get to meet interesting people who use graphs in surprising and creative ways. Finally, I would say that graphs are becoming more and more important, and this trend is likely to continue because there's a lot of untapped potential out there. However, it's not all rainbows and ponies, unfortunately. There are many factors that frustrate and hinder wider adoption of graphs. This includes technological challenges as well as social challenges. In a word, graphs are slow. One, they're slow to run. computers have been optimized for decades to operate on dense arrays such as NumPy. Hardware simply isn't designed to operate on graphs efficiently. And software struggles between the competing goals of being fast or being flexible or being easy to use. It's hard to have all three. 2, slow to be applied. It's often not obvious how to apply graphs to your problem or your area of expertise, and you may not know if it's worth the effort to learn. Say you watch a talk covering basic graph algorithms. You might walk away thinking, that's interesting, but it's pretty basic and doesn't seem very useful to me. Or you watch a talk that does dive deeper on something, a specific application. Chances are your eyes will gloss over and you might not understand a thing. If this happens to you, don't worry. It's not your fault and you're not the only one, because it probably wasn't your field or your problem. But things do go deeper. The problem then is that graphs are very abstract, and it's challenging to build a connection with an individual and take them far enough where they have an aha moment and they can finally understand, yes, graphs are useful to me. 3, graphs are slow to be embraced. Is this an essential literacy for you, your team, or your organization? Embracing it means that you or somebody made the strategic decision that graph literacy is essential to better understand your customers, your business, to sell your product, advance your science, or improve your engineering. How does GraphBLAS help? First, GraphBLAS is very fast. It is much faster than SciPy sparse arrays, and it's not even fair to compare it to NetworkX, which is a little slow. GraphBLAS is flexible. It provides building blocks from which to create custom graph algorithms in the language of linear algebra. GraphBLAS is scalable. It abstracts away how the computation is done. Implementations can run in parallel, use GPUs, and eventually run distributed on mini computers. That doesn't exist yet, but it can in theory. And GraphBLAS is a new way of thinking. It extends linear algebra to efficiently work on sparse data to solve graph problems. As you learn about GraphBLAS, come with an open mind. Whereas NetworkX is the most popular Python library, and for good reason. It has many algorithms, has great documentation and tutorials, and is trusted by a lot of people because it's been around a while and used. It's also pure Python, so it's easy to install and the code is easy to read, and lots of good reasons for that. However, even though NetworkX is flexible because it's pure Python, it's also very slow because it's pure Python. So what do NetworkX and GraphBLAS have in common besides doing graph analytics? They're both flexible. Great. So what if we combined them and got the best of both? The ease of use of NetworkX and the performance of GraphBLAS. Well, I assume if we do this, people will chase after us with bags of money because this is what they want. No guarantees, though. That may not happen. Time for some theory. Here, we encode the directed graph on the left as a sparse matrix on the right. Note that the diagram on the right shows the transpose matrix AT. This actually shows one step in a breadth-first search, A transpose V. We start at node 4, the red node in the graph, and the red dot in the vector V, and we use the matrix multiply to traverse the outgoing edges in green, thereby getting results for nodes 1 and 3 in blue. If you want to watch more about graphs in general, check out this recent video from PyCon 2022. It's pretty entertaining and has lots of original drawings. Check it out. But first, I have some important points about this diagram showing matrix multiply. The first point is that missing values in this matrix are not 0. Missing means missing, and the multiply part of matrix multiply ignores missing values. Second, we will actually want to customize what the matrix multiply actually does. And we do this using, drum roll please, Semirings. A semiring combines a monoid and a binary function. Of these, I'm sure you're most familiar with the binary function. It has 2 inputs of any type and has 1 output of any type. Here, we give our binary function money and a pet store, and we get back a cat. Wonderful. A monoid is a more specific binary function. The two inputs and the outputs must be the same type. Normal matrix multiply uses plus as the monoid and times as the binary function. We call this the plus times semiring. In single source shortest path, we use the min plus semiring, where we use min instead of plus and plus instead of times. There's more you need to know about monoids. In GraphBLAS, we only really care about commutative monoids, which means that the argument order doesn't matter. Monoids are also associative. Given three inputs, white cat, tabby cat, and calico cat, we can process them in any order and we'll always get the same results. A monoid also has an identity value. When the identity value is used with any other value, the monoid will return the other value. For example, if cutest cat is our monoid, then ugly cat is our identity. Because every other cat in our domain, when compared to ugly cat, is cuter. These three properties, commutativity, associativity, and having an identity, enables GraphBLAS implementations to perform matrix multiplies and reductions very efficiently. Common monoids are plus, times, min, and max. Whew. So what's next? We have nearly all the ingredients for creating something amazing. NetworkX provides the API, which we steal, and the tests, which we run. As a side note, it's actually really, really nice to have an existing test suite to test against. So our work really isn't that hard. Python GraphBLAS and GraphBLAS are rock solid and ready to use. Many GraphBLAS algorithms are already written in a hodgepodge of other languages and places. We just need to port them over to Python and adapt them to pass NetworkX tests. The main missing ingredient is help. Maybe that means you. If you need a faster graph algorithm for your work or research, please reach out and let us know. Or perhaps you're a student looking for a class or a thesis project. Better yet, maybe you're a teacher or advisor who can suggest such projects. Or maybe you're just like me and you like solving puzzles, especially when they can benefit the world. If we're successful, then we do have a plan where NetworkX can automatically use GraphBLAS algorithms to be faster. So if you call it NetworkX, you're using GraphBLAS algorithms. So best of both. Finally, we are a small but friendly group, and we're open to mentoring. Our onboarding experience is a work in progress, but we should continue to improve. So please be patient. If you're interested or just want to learn more, feel free to reach out, and you're welcome to join our weekly community call. That's it. Thank you.